Welcome to Week 7, Lecture 1, Introduction to Correlation. So far, we've discussed statistical tests that we can use for experimental designs. In other words, we've answered questions about situations where the experimenter manipulated the variables. For example, a z-test and t-test is a situation where the participants are assigned to a specific treatment group. In the independent sample t-test, the experimenter assigns individuals to either of the groups. In the dependent measures samples t-test, the experimenter administers the treatment between pre and post-test. And the same is true for the one-factor ANOVA. The ability to assign people to groups or control individuals' placement within groups is also known as experimental control. And the ability to have control over the variables and knowing that there are no significant characteristics that distinguish the two groups is what allows us to make inferences about our sample to the population. So in other words, it's the one that lets us generalize the information that we get from our samples to the whole group. There are situations where we are interested in doing a research study. However, the researcher lacks experimental control because they are unable to control how individuals get assigned to the groups of interest or the treatment groups. Can you think of a situation where the experimenter does not have the ability to control the variables? For example, if we're looking at a study of gender differences, we really can't assign an individual to a female versus a male group. In other words, the gender is already determined for us, and although we can split individuals by gender, we can't actually assign them to the group. So when you're comparing a group of men and female, there may be other things that distinguish the group between men and women other than just what you're trying to get at or what the experimenter is trying to control. So what if we want to know if there is a difference in physical health between smokers and non-smokers? If we were to do an experiment and randomly assign individuals to a smoking and a non-smoking group, we could then compare their scores on a fitness test to see if there's a difference in physical fitness. However, it is unethical to assign individuals to become smokers because of all the health issues associated with smoking. Alternatively, we can do an observational study where we find individuals that are already smokers and non-smokers and compare their fitness scores based on their previous smoking status. If you think back to week 1, we discussed type of experiments and the difference between observational and experimental studies. We typically obtain data from two distinct sources. In an observational study, we observe and measure specific characteristics, but we do not attempt to modify the subjects being studied. In an experimental study, we apply some treatment and then proceed to observe its effects on the subjects. The subjects in the experiments are called experimental units. An observational study there is one very important thing missing. Can you tell what's missing in an experimental study? It's random assignment. The logic behind randomization is to use chance as a way to create two groups that are similar. Although it might seem that we should not leave anything to chance in experiments, randomization has been found to be an extremely effective method for assigning individuals to groups. In other words, random assignment is used to ensure that the differences between the groups, in the case we just discussed, smokers and non-smokers, is due to the experimental manipulation and not due to chance. In an observational study, we cannot randomly assign individuals to one group, so we have to consider that the two group differences could be due to something else. For example, unhealthy people might be more likely to smoke. Thus, we need to learn a new statistical test to analyze observational studies. In this chapter, we are introduced to methods for determining whether a correlation or an association between two variables exists. A correlation is a statistical technique that is used to measure and describe a relationship between two variables. Usually, the two variables are simply observed as they exist naturally in the environment. There's no attempt to control or manipulate the variables. You should also notice that a correlation requires two scores for each individual. These scores are normally identified as X and Y. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. So we have to explore data. Before doing any formal statistics, we should do a scatter plot to explore the data visually. We can examine a scatter plot for any distinct patterns or for any outliers, which are points that are far away from all other points. This is very similar to when we were looking at assumptions of all the experimental tests that we've done in the past. If plotted points show a distinct pattern, we can conclude that a correlation exists between the variables. If there's no pattern, you can conclude the experiment at this point. So this is an example of a scatter plot, and it just has the data points for the x variable that correspond with the y variable. And in general, it's just a rule of thumb to put the x variable on the bottom and the y variable over here on the vertical axis. Okay. This figure shows a distinct straight line or linear pattern. We say that this correlation is positive between x and y since as the values of x increase, we find that there is a corresponding increase in the values of y. Thus, this is considered a positive correlation. This figure also shows a distinct linear pattern. We say that this is a negative correlation between x and y because as the x variables increase, the y variables decrease. So as you see, as the value here gets higher, what happens is that the values here are lower. At the beginning, where the values of the x variables are low, the corresponding y variable values are high. This figure is an example of a scatter plot that shows no distinct pattern and suggests that there is no correlation between the values of x and y. This scatter plot shows a distinct pattern suggesting that there is a correlation between an x and y. However, this pattern is not a straight line. There are specific characteristics of a correlation or of a relationship. A correlation measures three characteristics in terms of the relationship between x and y. And so here are the three characteristics. The first one is the direction of the relationship. In a positive correlation, the two variables tend to move in the same direction. Again, as the values of the x variable increase for one individual to another, the y variable also tends to increase. When the x variable decreases, the y variable also decreases. In a negative correlation, the two variables tend to go in opposite directions. As the x variables increase, the y variables decrease. In other words, this is an inverse relationship. Also, the direction of the relationship is identified by the sign of the correlation. A positive value indicates a positive relationship, a negative value indicates a negative relationship. The book gave us a really good example in terms of if you ran a concession stand in a football stadium. What you would find is that there is a relationship between the temperature and the amount of cold drinks that you sell. As the temperature becomes hotter or higher, you tend to sell a lot more beer. As the temperature gets lower, you sell relatively little beer. This is an example of a positive correlation. you would probably see the same kind of relationship between temperature and the sale of hot drinks as well. Okay, so now the next characteristic of a correlation that we're going to discuss is the form of the relationship. So in the preceding example, we talked about coffee and beer. The relationships tend to have a linear form. That is, the points tend to form a straight line. The most common used correlation is used to measure straight line relationships. In other words, linear relationships. I'd like to note that there are other forms or other relationships that can exist between two variables, and those are special types of correlations that we use to measure them. The linear correlation coefficient, or R, measures the strength of the relationship of a linear correlation between a pair of x and y variables. And so here's an example of a linear relationship between the variables of x and y. For linear correlations, we can identify an equation that best fits the data, and then we can use that equation to predict the value of one variable given the value of the other variable. We also present methods for analyzing differences between predicted values and actual values. We're going to go into more depth on this into the next lecture. The last characteristic of correlation that we will discuss is the degree of the relationship. Finally, a correlation measures how well the data fit a specific form being considered. For example, a linear correlation measures how well the data points fit onto a straight line. The degree of the relationship is measured by the numerical value of the correlation. A perfect correlation is always identified by a value of 1, and that indicates that the data fit perfectly. So you can see this is a good example of a linear correlation with an R value equal to 1. And as you get a certain increase in your X variable, you get a corresponding increase in your Y variable. So they increase in the same amount every time. If you were to draw a line between these points, you could see that it is quite easy to draw a line, which indicates that there is a good fit. The other benefit to a good fit linear relationship has to do with your ability to predict values. For example, what if this data point was removed? It no longer exists. The question is, would you be able to guess where that point belongs? And so let's say we were missing a data point and we wanted to put it back in or predict where that data point belongs. Would you guess that it would be here or here or here? If we didn't know anything about the relationship, that point could be anywhere on this plot. However, because we know that this is a linear relationship, we can pretty much predict where that point would be. Because the increase here is consistent across the two variables, we could predict that if we had a variable value for 40, we could predict that the corresponding value for the y variable is also 40. At the other extreme, a correlation of 0 indicates that there is no fit at all. In this example, or in this scatter plot, excuse me, we look at the data points and we see that they are dispersed and you can't really distinguish a pattern. So if we were to try to fit a line in this relation, trying to fit a line to this relationship can be very difficult. You could draw a line like this, which seems to fit pretty well. However, this line fits about just as well. And the thing about this is that the lines show very different relationship. One was showing a positive relationship. This one's showing a negative relationship. This line can be just as good. And so can this final line. The problem with a data set that doesn't show a very strong relationship or a strong degree of relationship or a strong fit is that you can draw a multitude of lines that fit equally as well. And the real issue, though, is you cannot really make any kind of predictions like we did with with a really strong correlation because depending on which line, your predictions could be very different. Where and why correlations are used. Although correlations have a number of different applications, there are a few very specific examples that I'm going to present to give an indication of when we generally use correlations. The first, correlations are often used for predictions. I even alluded to it in earlier slides. If two variables are known to be related in a systematic way, it is possible to use one of the variables to make accurate predictions about the other. So, for example, when you did your admissions application for college, you were required to submit a great deal of personal information, including your scores on the SATs. Colleges want this information so that they can use this score to predict your success rate in college. SAT scores and college grade point averages are correlated. So based on this relationship, college admissions office can make predictions about the potential success of each applicant. Correlations are also used to test validity. We can use a correlation to see if a test is truly measuring what it claims to test. So how can you show that a test is truly measuring what it claims? Well, that is, how could you determine the validity of a test? One common technique for demonstrating validity is to use correlation. If the test is actually measuring what it claims, then the scores on the particular test should be related to other tests or measures that measure the same thing. So, for example, if I developed a new test that measures IQ, I could take an individual score on my test and compare it to a standard IQ measure, like, for example, the Stanford Binet test for intelligence. And if both tests measure the same thing, then they should be correlated. So a psychologist could measure the correlation between a new test and each of the other measures for a previous test in order to demonstrate that the new test is valid and it is measuring what we claim the test to be measuring. We can also use correlations to test reliability. Correlations are often used to determine reliability. Procedure is considered reliable to the extent that it produces stable and consistent measurements. One way to evaluate reliability is to use correlations to determine the relationship between two sets of measurements. When reliability is high, the correlation between the two measurements should be strong and positive. Lastly, we can use correlations for theory verification. Many psychological theories make specific predictions about the relationship between two variables. For example, a theory may predict that there is a relationship between brain size and learning ability. A developmental theory may predict a relationship between patients' IQ, between the parent's IQ and the child's IQ. A social psychologist may have a theory predicting the relationship between a personality type and a behavior in a social situation. In each of these cases, the prediction theory could be tested by determining the correlation between these two presented variables. Now let's talk about the properties of the linear correlation coefficient R. The value of R is always between -1 and 1 inclusive. Another way you can write it is R is greater than or equal to -1 and is less than or equal to 1. If all the values of either variable are converted into a different scale, the value of the R does not change. The value of R is not affected by your choice of X or Y. Interchange all the X and Y values. The values of R will not change. The R measures the strength of a linear relationship. It is not designed to measure the strength of relationships that are not linear. And lastly, R is very sensitive to outliers. That is, a single score, one outlier, can dramatically affect the value of R. I mentioned earlier that before doing any statistical test, we should use a scatter plot to explore the data visually, and we can examine the scatter plot for any distinct patterns. One might wonder, if we can see a pattern, couldn't we just report the pattern and be done? And the answer is no. Because conclusion based on visual examinations of the scatter plots are largely subjective, we need more objective measures. Thus, we need to use linear correlation coefficient R, which is useful for detecting straight line patterns. Because the linear correlation coefficient R is calculated using the sample data, it is a sample statistic used to measure the strength of a linear correlation between X and Y. By far, the most common correlation coefficient that we'll be using is the Pearson correlation. There are other correlation coefficients, but for the purpose of our class, we'll only cover the Pearson correlation coefficient. The correlation coefficient measures the degree and the direction of the linear relationship between two variables. Another way to think about it is that R measures the relationship to the degree with which X and Y variables vary together divided by the degrees in which X and Y variables vary separately. This should be very similar to you if we think back to other test statistics that we've done, where we looked at differences between the groups divided by error. Very similar thing. When there is a perfect linear relationship, every change in an X variable is accompanied by a corresponding change in a Y variable. In the case where the covariability X and Y together is identical to the variability of X and Y separately, the formula will produce a correlation of 1 or -1. And this value will indicate a strong linear relationship. If the value is 1, that indicates that we have a positive linear correlation. So as the variable X increases, you'll find a corresponding increase in the variable Y. You could also have a negative R value, like a -1, which would also indicate a strong linear relationship, but it would indicate a strong negative linear relationship. As the variables of X increase, the variables of Y decrease. At the other extreme, when there is no linear relationship, a change in the X variable does not correspond to any predictable change in Y. In this case, there is no covariability and the resulting correlation is 0. And here is an example of a situation where we really have no relationship between X and Y. Now on to the fun part, calculating the Pearson correlation. Okay, so I know that for most of you this is probably not the fun part, but I think that after calculating some of the stuff that we've done for the ANOVA, you might find the correlation a little bit refreshing. So, whenever you calculate a correlation in the real world, you'll probably do it using some statistical package or software package. We're going to, of course, be using Excel to calculate it. But in a situation when you have to calculate it by hand, this is the formula that's recommended that you use. Okay, and I know it looks big and scary, and so what I'm going to do is I'm going to break it down into parts, but in essence, this is the formula that we're going to be using for the Pearson correlation coefficient. So I'm going to go ahead and break this formula down, and on top of this we have the sum of product deviations, and so we will start talking about the sum of product deviations. Remember, this refers to the degree to which the X and Y variable vary together. So the sum of product deviations, to calculate the Pearson correlation, it's necessary to introduce this new concept, the sum of product deviations, or SP. Now, this is a very similar concept to the sums of squares, which we use to measure the variability for a single value. Now we use SP to measure the amount of variability or covariability that exists between two variables. The sum of products is equal to the sum of every X variable multiplied by every Y variable, subtracted by the sum of every X variable multiplied by the sum of every Y variable, divided by the total number of participants. If you look at the formula for the sums of squares, you'll notice that this is actually quite similar, except for in this value, you multiply x by itself, whereas here you multiply it by the other variable. I'm going to talk a little bit more about this in a minute. But I'd just like to point out, now that we have the formula for SP, or the sum of products, we can now actually compute, we know everything that we need to know to compute the value of R. Because now that we know how to compute the sum of products, we know already how to compute the sums of squares, we should be able to go ahead and fill out the formula. Let me just point something out though. If we were to take the formula for SP and plug it in on top, and then we go ahead and multiply out the value of n, what you will find is that the formula for SP is exactly the value in the formula that we have presented in the book and the one that I had presented at the very beginning when we talked about the Pearson correlation. So you'll see that this value is the same as this, which is the same as this, or the same as this. And again, the same is true. This is just the sums of squares of y, and this is the sums of squares of x. Now, I prefer using this formula simply because it seems a lot less overwhelming looking at it as the sum of products over the square root of the sums of squares of x and the sums of squares of y. It's what I've been familiar with throughout this whole course, so I'm more familiar with it. You can, of course, write out the formula in any which way you prefer, whatever is easier for you. Okay, so now let's go ahead and apply what we've learned today and throughout our course and do an example of a correlation. So here we have a set of data. We have our x and our y variables, and now we simply need to use those values to compute an R value. So here's our formula for our R values. So to complete this formula, we need to get the sum of products, the sums of squares for x, and the sums of squares of y. So I'm going to go ahead and list those out. So we need the sum of products, the sums of squares of x, and the sums of squares of y. So we're going to go ahead and start by computing the sum of products of deviations, or SP. First, we're going to go ahead and compute x multiplied by y. And if you think back to our sums of squares, this means that we take every value of x and we multiply it by y. So I'm going to go ahead and start a column over here in my data set. And then I'm just going to multiply across. So the value of 1x multiplied by 3y is 3. 2 times 6 is 12. 4 times 4 is 16. And 5 times 7 is 35. I'd like to just stop here and note, of course, I'm expecting you guys to do this math and to maybe even just stop the presentation and try to do it on your own. It always helps doing it that way. I know I've been saying it this whole time, but it doesn't hurt to repeat myself one more time. And so we go ahead and add up all those values, and now we have the sum of x multiplied by y. So we go ahead and place that in the formula, and next we're going to go ahead and get the sum of x, and we just simply add up all the x values and get a sum of 12. We'll go ahead and place that in the formula, and now we need to go ahead and compute the sum of y. So we go ahead and add up all the values in the y column, and we get a value of 20. We place that in the formula, and now we just have to come up with our value for n. And that's pretty simple. N is the number of scores that we've obtained, or the number of participants. And in this example, we have 1, 2, 3, 4. So we have 4 score pairs. That's another way to think about it. So we go ahead and place that in. And now we simply solve for SP, and we get a value of 6. So we go ahead and place that up here at the top. I like to always use some kind of a formula that, or table or chart, so we can keep track of all our values. I find that it always helps us out in the long run to not confuse where things come from. Next, let's go ahead and compute the sums of squares, and this should be pretty straightforward. We've done this many times, so we just need to take every x value and square it. Then we need to take the sum of x and multiply it by the sum of x over the number of score pairs that we have. So we already know the sums of x and the number of square pairs that we have, so we can go ahead and put those values in our formula already. And now we just have to calculate the sum of x squared. So we just need to take every x value, multiply it by itself, and then add those. So we're going to go ahead and start a column for x squared. And I'm not going to go in step by step with this because we've done this many times throughout this term. And so if you want to calculate these values on your own, this would be a great time to go ahead and pause the presentation. Here are the values for x squared. And now we just need to add them up. And we get a sum of 46. So we go ahead and place that formula. And now we solve for the sums of squares. And we get a value of 10 for sums of squares x. And we go ahead and place that in at the top. Okay, now let's go ahead and solve for sums of squares y. And again, we just get the same values that we've already obtained. They're in the table. So I'm going to fill those in. And now we simply need to get the sum of x squared. So, the sum of y squared. So what we need to do is add another column. And we have our y squared column. Again, this is a great time for you to pause the presentation if you want to work along with me and get these values. And so here are the values that I have for y squared. And now we just simply need to add. And so we get 110 for our sum of y squares. And we just need to plug that into the formula. And now we just solve for the sums of squares y. And we get 110 minus 100. Giving us a value of 10 for the sums of squares y. And now that we have all these values, we can go ahead and bring up our formula. And here we have it, and we just have to plug these values in and solve for r. And we get a value of 0.6 for r. And that's how we calculate our r squared. Not too hard a concept considering some of the stuff that we've done so far. Okay, so the calculation of the Pearson correlation. The Pearson correlation consists of a ratio comparing the covariability of x and y, which is what we have in the numerator, with the variability of x and y separately, which is what we have in the denominator. We will use the sum of products to measure the covariability of x and y, and the variability of x and the variability of y will be measured by using or computing the sums of squares for the x scores and for the y scores separately. So what we're really looking for when we're looking at the R ratio is we're looking at the covariability of x and y, or SP, over the variability of x and the variability of y separately. And this, of course, is the same as the formula that we have in the book that's strongly recommended for us to use. So I hope that you have enjoyed our introduction to correlation, and we will, I guess, meet again later this week. Thank you very much, and you have a good day.